Sweet Briar is excited to provide this opportunity for the Central Virginia engineering community to come together and celebrate engineering. We are proud to be one of 2 women's colleges with an ABET accredited engineering program, and we are committed to increasing diversity in engineering. Through our Explore Engineering events, more than 500 high school women have worked on creative, team-based design projects as a part of weekend or week-long events. Our graduates now work in a variety of areas of engineering across the country. More locally, our graduates have worked at AMTI, BWX Technologies, Framatome, Glad Manufacturing, Novatech, Delta Star, Go Measure 3D, Lynchburg City Water Resources, and the National Ground Intelligence Center. We are so thankful to the vibrant engineering community here in Lynchburg that has supported our graduates in internships and employment, worked on our engineering advisory board, and collaborated with us on capstone design projects. As eWeek is all about ensuring a well-educated future workforce, I'd like to acknowledge several groups of students as well as local upcoming science and engineering events. And if you could please stand when I name your school or other associated facility, please do so. We had 12 high school students participate in Sweet Briar's Introduce a Girl to Engineering activities this afternoon. If you could please stand if you did that with us. Thank you. Thanks. We have students from regional elementary, middle, and high school here tonight as well. Good stand. We have college students from, of course, Sweet Briar College, the University of Lynchburg, Randolph College, VMI, Liberty University, and Virginia Tech. If you could please stand as well. Thanks. As for upcoming events, the Science Festival of Central Virginia, run by Randolph College, has events on March 14th, the Pie Run, as well as March 21st through 24th, including a Maker Fair sponsored by Vector Space. So several companies are represented here tonight. Specifically, I'd like to call out Google, Navarre, Liberty University, Novatech, Randolph College, Wiley Wilson, and the Center for Advanced Engineering and Research. Please make sure to stop by their displays in the back of the room. Before we move on, I would like to thank Rebecca Gerton for her hard work in making sure that everything went up. Our wonderful staff of Meriwether Godsey for providing dinner tonight. And Sweet Briar's physical plant for plowing all the roads. So I am now proud to introduce Yasmin Bekri, who will introduce our speaker of the evening. Yasmin was born in Ethiopia, raised in Botswana, and more recently is from Alexandria, Virginia. She is a junior engineering major here at Sweet Briar. As a transfer student from Northern Virginia Community College, she brings expertise in architectural engineering and green design. In college, she has been extensively involved in the Student Government Association and has worked as a peer tutor and student ambassador. This year, she has initiated a research project to design and build solar-powered charging and study stations for the Sweet Briar's campus. Yasmin is also a member of the Phi Theta Kappa Honor Society. And when she is not busy with schoolwork or research, she likes arts and crafts, hiking, and painting. So please join me in welcoming Yasmin.
Thank you, Dr. Brinkman, for the introduction. Good evening, ladies and gentlemen, and welcome again to the 2019 Engineering Banquet hosted by Sweet Briar College. I'm honored and excited to introduce this year's guest speaker, the renowned theoretical physicist and Nobel laureate, Dr. Kip Thorne. It is indeed a great privilege to have him join us here at Sweet Briar College as we celebrate Engineers Week and specifically introduce a Girl to Engineering Day, a community celebration that aims to inspire more girls to continue to shape the world around them through engineering and technology. It would take me the whole evening, if not longer, to do justice to Professor Thorne's long list of accolades. And I know you've traveled from near and far through this horrible weather to hear him talk, so I'll keep this introduction brief. A native of Logan, Utah, Dr. Kip Thorne is the Feynman Professor of Theoretical Physics, Emeritus at the California Institute of Technology, where he received his bachelor's degree in physics in 1962. He then earned his PhD degree from Princeton University in 1965 and returned to teach at Caltech the year after. During his time there, he led a research group working on relativistic astrophysics and gravitational physics, with emphasis on relativistic stars, black holes, the theory of time travel, and particularly gravitational waves. Under his mentorship, 53 students received their PhD degrees. And throughout the years, Professor Thorne co-authored the textbooks Gravitation in 1973, Modern Classical Physics in 2017, and was the sole author of Black Holes and Time Warps, Einstein's Outrageous Legacy in 1994. In 1984, he co-founded the Laser Interferometer Gravitational Wave Observatory, or LIGO project, along with Professors Rainer Weiss and Ronald Rever, colleagues from MIT and Caltech, respectively. Physicists from all over the world collaborated with Professors Thorne and Weiss and LIGO director Barry Barish in the development of the revolutionary laser wave detector that enabled the observation of the universe's gravitational waves for the very first time in 2015. This observation confirmed a prediction that Albert Einstein had made in his general relativity theory about a century earlier. After decades of work, this groundbreaking discovery was called a marvel of engineering and led to global advances in astrophysics and gravitational physics. In 2017, it earned Dr. Thorne a shared Nobel Prize in physics, a success that he has attributed to the result of the efforts of a team of 1,000 people. In 2009, he stepped down from his Caltech professorship to focus on a new career at the intersection of art and science. This has included research on geometrodynamics, the nonlinear dynamics of warped space-time, Christopher Nolan's 2014 blockbuster movie Interstellar, which was derived from a treatment that Professor Thorne co-authored and for which he was executive producer. His 2014 book, The Science of Interstellar, and recently, a new secret movie project, a collaboration with composer Hans Zimmer and visual effects guru Paul Franklin on multimedia concerts about Professor Thorne's forthcoming book, The Warped Side of the Universe. This will be composed of paintings by the artist Leah Halloran and poetic prose by Professor Thorne himself. Can you believe that this is not even the exhaustive list of his accomplishments? Dr. Kip Thorne is many things: a theoretical physicist, a professor, an author, a Nobel laureate, an executive producer, an artist, just to highlight a few. But overall, he is a living testament of what it means to persevere through life's challenges and be the very best version of yourself. Moreover, he continues to inspire generations of engineers and scientists to redefine the limitations. So without further ado, it is with great pleasure that I ask you to join me in welcoming our guest speaker, Dr. Kip Thorne.
Thank you, Yasmin. Can you hear me? It's true that I've worked in a lot of different areas, but the reason is closely related to an ancestry that I share with Professor Timothy T.C. Scott, who is here today and who played a big role in my coming, my dear friend and cousin. Our grandfather Newell Comish, told me when I was 4 years old that if I found something to do as an adult that was like play, I will have succeeded in life. And so I think I've succeeded. I believe this very much to my heart. When you become an adult, you really should try to find something that you devote yourself to that not only may be important, but also is a lot of fun. And so here I am. This is what I've been doing. I want to talk about the creation of gravitational wave astronomy. It's the work for which the team with which I collaborated should have gotten the Nobel Prize, although it went to just 3 of us. It has been a collaboration between engineers and physicists, and I want to emphasize engineering and physics joint collaboration aspects of this. 1.3 billion years ago, here on Earth, multicell life was just forming and spreading over the globe. But at that same time, in a galaxy far, far away, 2 black holes circled around and around each other. And you see them here on the screen from a computer simulation. I know that some people in the back may not be able to see the visuals very well. Don't hesitate to move your chairs up here closer if you want to. As the 2 black holes went around each other, this is what it would have looked like to your eyes if you had been there. They spiraled together, collided, and produced a gigantic burst of gravitational waves. These gravitational waves, whose character I'll describe in a few minutes, propagated out into from the galaxy in which the 2 black holes lived into the great reaches of intergalactic space. They propagated across intergalactic space and traveled for 1.3 billion years until 50,000 years ago, when here on Earth our ancestors were sharing the world with the Neanderthals. At that point, these waves reached the outer reaches of our own Milky Way galaxy. For 50,000 years, they traveled through our Milky Way galaxy, and they arrived at the Earth on the 14th of September in 2015, just 3.5 years ago. They arrived at the Earth, first touched down at the Antarctic Peninsula, the tip of the Antarctic Peninsula. They traveled upward through the Earth, unaffected by all the matter inside the Earth, and emerged from the Earth in Livingston, Louisiana, sort of halfway between New Orleans and Baton Rouge. And there is where our Laser Interferometer Gravitational Wave Observatory, or LIGO, one of our facilities, lives. 7 milliseconds later, they emerged through the Earth at Hanford, Washington, our other LIGO gravitational wave detector. The data that came from this, our detector saw these waves, the detector analyzed these waves, and that were fed into a team of over 1,000 people spread around the world as part of the LIGO-Virgo collaboration. These are just a few of the members of the scientists and engineers in this team. For about 4 months, the team set and analyzed the data, trying to be absolutely sure that this really was gravitational waves that we were seeing. And then when we were absolutely sure, we announced it to the world on the 11th of February, 2016. And it made front page news, front page headlines in all of the major newspapers around the world. Now, how did we get here? The story begins with Albert Einstein. In 1915, he formulated his general theory of relativity, which is a set of physical laws that say that gravity is produced by a warping of space and time, and that say that space and time are warped in very interesting ways. And the following year, in 1916, he predicted, using the equations of his relativity theory, he predicted the existence of gravitational waves. What these waves do, you can understand by imagining going out in space, lay down a rectangular grid of particles. The particles are all at rest with respect to each other, and then as the wave passes through them, going perpendicular to the plane in which you have laid them down. I'm having a little trouble with my remote. The waves push the particles apart along one direction and squeeze them together along the other direction. It's You can think about this in two different ways. You can say that it is a stretching and squeezing of space, oscillatory manner, or a better way to say it is that the inertial reference frames here and there, and the particles over here remain at rest in the inertial reference frame, particle over there remains at rest in the inertial reference frame. Those inertial reference frames move back and forth with respect to each other. So that's the essence, the sense in which space is stretched and squeezed. These waves then were predicted by Einstein in 1916, but Einstein then says in his prediction paper that the waves will be so weak that it's unlikely humans will ever be able to see them. And so it was not until the 1960s, about 50 years later, that anyone really even tried because it was so daunting. The first person to try was Joseph Weber, an electrical engineer at the University of Maryland. After he got deep into the project, he moved over into the physics department. But the reason he was able to pull this off was he had the training of an electrical engineer. Electrical engineers started this field. Electrical engineers started radio astronomy. Engineering really is the foundation for building the instruments that we use to explore the universe. And it is the engineers who played a crucial role in this effort as well. The reason that Joseph Weber was launched off in this is twofold. First, that we now understood more about possible sources of gravitational waves that Einstein had never dreamed of, black holes and neutron stars, which would emit much stronger waves than anything Einstein knew about. And second, we had new technology, lasers, computers, and so forth, which made it plausible to be able to build a detector to succeed in detecting these gravitational waves. I was inspired by Joseph Weber. I knew him as when I was a graduate student at Princeton. And so when I went to Caltech, I started a theory group. I'm a theorist, not an experimenter. A theory group working on black holes, neutron stars, and gravitational waves. And among the things that I and my students did was began to develop a vision for what we might be able to do with gravitational waves in astronomy, a vision for what is now called gravitational wave astronomy. In 1972, we wrote our first technical paper describing this vision for the future of gravitational wave astronomy. And the key thing underlying this vision is the great contrast between electromagnetic waves, which are the type of wave which we have always used up until now to study the universe. That includes, of course, light, radio waves, X-rays, gamma rays, infrared, ultraviolet, and so forth. And gravitational waves. Only two types of waves. According to the laws of physics, there are only two types of waves that can be produced in the distant universe and travel to the Earth, bringing us information, the electromagnetic waves and the gravitational waves. Galileo started electromagnetic astronomy. Our goal was to start gravitational wave astronomy. The electromagnetic waves then are oscillations of the electromagnetic field that propagate through space as time passes, whereas gravitational waves are oscillations of the very fabric, the very shape of space and time. Electromagnetic waves in astronomy are almost always incoherent superpositions of emission from individual particles, atoms, and molecules, whereas gravitational waves are emitted coherently, the bulk motion of large amounts of energy and mass. Electromagnetic waves in astronomy are all too easily absorbed and scattered between their source and the Earth, and so we see only a small fraction of the universe because of intervening dust primarily, that prevents us from seeing things. Whereas gravitational waves are never significantly absorbed or scattered, not even if they're emitted in the Big Bang birth of the universe, and travel to the Earth from there. So this huge difference between these two types of waves told us that first, many sources of gravitational waves would not be seen with the standard electromagnetic telescope, and that was the case of colliding black holes. We have seen no electromagnetic waves from the colliding black holes. We would not know there were colliding black holes if all we had was electromagnetic detectors, electromagnetic telescopes. Gravitational wave telescopes were necessary for that. Second, because all of our present knowledge, almost all of our present knowledge of the universe comes from electromagnetic waves, and gravitational waves are so different, huge surprises are likely as we open up gravitational wave astronomy. And finally, then, gravitational waves have a potential to revolutionize our understanding of the universe in the same way as Galileo's telescope and the many generations of electromagnetic telescopes that followed have revolutionized our understanding of the universe. So that was the motivation. In the same year as with the student Bill Press, I wrote this technical paper with the vision for electromagnetic astronomy. My friend Ray Weiss at MIT invented a new kind of gravitational wave detector. And this gravitational wave detector involved having 4 mirrors that hang from overhead supports. On the screen, you see them as looking down on them. And so you have 2 mirrors along that and 2 mirrors along another arm that's perpendicular to the first arm. And as the gravitational wave comes along, it pushes, and these mirrors hang from wires or fused silica fibers today from overhead supports. As the gravitational wave comes along, it pushes the mirrors together along one arm, pushes them apart along the other arm, then pushes them together along that arm and apart on the first arm. And Ray's idea was then that you send laser light in through a beam splitter. Half of it goes into each of the arms. The light is guided so it bounces back and forth in the arms many, many times, and then it comes back and recombines the beam splitter. And as the mirrors are pushed together along one arm and apart along the other, the interference of the light at the beam splitter changes. And as a result, the intensity of the light that's going at output direction, which is down on the screen, the intensity of that light oscillates up and down as the wave passes. So that oscillating intensity of the light is your gravitational wave signal. So that was the basic idea that Ray had. He called this a gravitational wave interferometer, or gravitational wave detector. I looked at this. I was in the midst of just finishing writing a textbook on gravitation together with Charles Misner and our PhD advisor, John Archibald Wheeler. We were about to go to press, and so I didn't have time to study Ray's paper. I didn't have time to talk to him, but it was obvious to me that Ray had lost his mind. There was no way this was going to work, and so I had a very mild statement that I wrote in this textbook just before we went to press. This is not promising. And why did I think it was not promising? And just look at some numbers. So first, we measure the strength of the gravitational wave by its strain. It's the amount of strain as an engineer understands it in space as space stretches and squeezes. If you have the distance between these 2 mirrors as being L, and the motion back and forth, the displacement is delta L, the ratio of the displacement to the distance is the strain. And that strain, according to the predictions that my colleagues and I were making based on our understanding of sources of gravitational waves in the distant universe, a strain of 10 to the minus 21. That's a kind of a small strain. That meant that if we had mirrors that were about 4 kilometers apart, as we now have in our LIGO gravitational wave detectors, the motions would be about 10 to the minus 17 meters. Now, just how big is 10 to the minus 17 meters? Let me remind you, even though you're engineers and you sort of know it, you may not know it in your gut without looking at this carefully again. So begin with about 1 centimeter. Divide by 100, you get the thickness of a human hair, 100 microns. Divide by 100 again, you get the wavelength of the light that's being used. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, you get the motions that I and my colleagues were predicting you would have. To think that you could use light to measure a motion that was approximately 1 trillion times smaller than the wavelength of the light, that was this tiny, to measure these gravitational waves, that was just incredible, and I couldn't believe it. Until I had long conversations with Ray Weiss and others, and I studied Weiss's paper in detail, and I became convinced. And I decided this was so important that I would do everything that I and my theory students could possibly do to help the experimenters pull it off. And so here I am today. I spent the rest of my career eating crow over my initial skepticism. Let me just give you one set of numbers to give you some sense of this as engineers. Suppose you bounce the light back and forth 100 times. That means you have a gravitational wave signal that's pushing the mirrors back and forth by 10 to the minus 17 meters But after the light has bounced back and forth 100 times, the effective displacement is 10 times bigger, or 10 to the minus 15 meters. So that's what's got to be measured. And can you do it? Well, one obstacle is photon shot noise, the randomness in the arrival of the photons at the output photodetector. And this randomness is described by a random walk. Well, it's a Poisson distribution for engineers. But in random walks, such as a Poisson distribution, the randomness goes like 1 over the square root of the number of photons that you use to make your measurement. And so it turns out that if you're really clever, the accuracy you can make a measurement with in the face of the shot noise is the wavelength of the light divided by 2 pi, 1 over the square root of the number of photons. If you're using a laser that has a few watts output, and you're looking for gravitational waves that oscillate, or say 100 oscillations per second, this turns out you've got in, say, 100th of a second, 10 to the 18 photons. The square root of that is 10 to the 9. You put the numbers in, you get noise of 10 to the minus 16 meters. It's 10 times smaller than the signal. That doesn't mean you can really do it. It just means, in principle, it's possible if you're really, really, really clever. But there are an enormous number of things that can go wrong, and that's why it required, in the end, a team of 1,000 people to pull this off, because there were so many things that could go wrong. Having seen that this was really possible, then we created a experimental group working in this field at Caltech. We brought Ronald Drever from Glasgow, Scotland there. Why? Well, he was very clever. He had invented a number of improvements on Weiss's basic idea. Most important was he would have the light go back and forth between the mirrors with all of the spots of light superposed on each other. In other words, he would put the mirrors separated in such a way that as the light went down and back, it would superpose coherently on itself. So an integral number of wavelengths down and back. And that meant that light would resonate between two mirrors in what we call a Fabry-Perot cavity. And so you would send the light in through the back of a mirror. It would get trapped between the two mirrors, and it would get stuck in there for 100 bounces and then leak back out. And that just meant that you didn't have the humongous number of spots around here. It could be a much more compact mirror and much more versatile, it turned out in the end. And so that was a huge improvement. And so we started then building a 40-meter prototype at Caltech. But in the meantime, at MIT, they finished Ray Weiss's 1.5-meter prototype interferometer. And more importantly, they carried out at MIT a feasibility and cost study for interferometers that would be a few kilometers in size. And this was a big deal. The crucial issue is that there are so many, again, I said there are so many things that could go wrong that you really had to get a handle on these and on how they could be solved from an engineering point of view. Now, what's the difference between an engineer and a physicist? Engineers cannot afford to make a mistake because people's lives depend on it frequently. You build a skyscraper, if it falls in an earthquake, people die. Physicists, lives don't depend on it. But on the other hand, if you're building something like LIGO that in the end is going to cost $1 billion, people's lives may not depend on it, but that's an awful lot of taxpayer money that you're responsible for, and you better get it right. And so again, we needed the security that an engineer brings in, the culture that you cannot be making mistakes in how you carry things out technically. And so this study of the feasibility and the costing was done by 3 physicists at MIT, 1 at Caltech, together with a team of 10 engineers from an industry at Arthur D. Little and 10 engineers at Stone and Webster. Let me just give you a sense of what had to be studied, the issues that they faced. This is just a tiny fraction of the things that were faced. So if you have air in that laser beam, as the light's bouncing back and forth between the mirrors, fluctuations in the number of air molecules that the laser beam encounters, with each air molecule slowing the light down just a little bit because of dispersion. Fluctuations in the number of air molecules will cause a fluctuation in how long it takes the light to go down and back. and will, as a result, do the same thing as a gravitational wave does. And so you can't afford to have very much air in there. So, of course, you have put the laser beam inside a big vacuum pipe. But then you face the fact that the worst kind of air molecule to deal with is hydrogen. Why? Because hydrogen, much more than any other molecule, when light goes through it, it slows the light down. It just turns out it's more polarizable than other molecules. And by the technique that steel is normally made, it leaves huge amounts of hydrogen inside the steel. That hydrogen can leak out over a period of years and cause us tremendous headaches and make LIGO fail. So they had to conceive, how do you make a whole new way of getting rid of the hydrogen in the steel in the manufacturing process, and that had to be a collaboration between physicists and engineers working in the steel industry. So a very special way of making steel had to be devised. And then there was the issue of all the construction costs and all the things that had to be. So these were among a tiny fraction of the things that were studied. Based on that feasibility study and costing study at MIT, and they work with prototype detectors, small detectors up to 40 meters in size, in Garching, Germany, in Glasgow, Scotland, at MIT, and at Caltech. In 1984, we proposed as an MIT-Caltech collaboration to build LIGO. And from 84 to 87, we continued our R&D, preliminary design studies, searched for sites, did site surveys of possible locations we would build these things. And the project was run jointly by Ray Weiss, Ron Drever, and me. We were the most dysfunctional leadership that science has ever seen. It was a disaster. And so we were told in no uncertain terms, but we knew it deep in our guts. We had to get a single director to pull this off. And this is a thing that I learned. If you're doing a big science or technology project, you have to have a single director who has ultimate authority and who knows how to collect information from lots of different places, people who are working within the project, and then make ultimate decisions in collaboration with the members of the team. And so we brought on board a guy named Robbie Vogt, who had been the first chief scientist at the Caltech Jet Propulsion Laboratory, very skilled at this. He hired 25 more engineers and physicists, primarily engineers, because we were mostly physicists at that time. And he paired each physicist with an engineer, working on the project jointly together. I was paired with Geraldine Billingsley, who was the lead optics engineer. And with Geraldine, we studied issues of light that gets scattered off of a mirror, goes and hits the wall of the vacuum pipe, goes back to the next mirror, scatters back into the next mirror, and it scatters back into the main beam. And if the vacuum pipe is vibrating, this tiny bit of light changes how far it travels. It gets mixed together with the rest of the light, but that can be a big change in how far it travels. And we're dealing with tiny changes due to gravity waves, and so that can mask any gravitational wave. So that was a problem. This gives you an example of the things that can go wrong, and this was our job to figure out how to deal with this with baffles, very specially designed baffles, which got installed. This is the photograph that appeared on the front page of the New York Times of the Discovery. This is a guy in there getting ready to install a baffle inside there to control scattered light. So here I am a theoretical physicist, but I'm paired with a superb engineer who really understood the optical issues to try to figure out how are we going to deal with this and design instrumentation to deal with it. So, Tim, I'm not just totally a theorist. I actually thank you, Tim. Let me just go on. So in 1989, we made a proposal for constructing LIGO to the U.S. National Science Foundation under Robbie's leadership. And we said we will first build the facilities, the vacuum pipes, and all the buildings and so forth. Then we would have a two-step strategy. We would build initial interferometers that would not see any gravitational waves, or are unlikely to. If we were really lucky, they would see them, but probably not. And then we would build advanced interferometers that would very probably see the waves. Why do it in two steps? Because we weren't smart enough to know how to build the real thing without getting our feet wet with simpler versions of the interferometers first. Now, this was never been done in astronomy before. You build something for $300 million, the initial interferometers, and you don't see anything. and then you upgrade for what in the end turned out to be another $600 million, and then maybe you see something. It took us 3 years to get approval under the circumstances. We were fought tooth and nail by many astronomers who would rather have seen that go into electromagnetic astronomy. But in the end, we managed to convince NSF and Congress to buy into this strategy, this two-step strategy. And once we got our initial funding for these instruments in 1992, Congress backed us, whether Republicans or Democrats, year after year with no substantial budget cuts until we succeeded in 2015. What's that? That's 23 years later. Is that 23 years later? And when we did succeed, the Republicans and the Democrats in Congress were as pleased as anyone. They take great pride in having backed this highly important but very difficult project all the way through. We brought on, when we began construction, Barry Barish, another professor at Caltech, to lead the effort because he had much more experience in running big projects than Robbie Vogt did. And he oversaw and worked out the organizational strategy, the construction of the facilities, and then he created something called the LIGO Scientific Collaboration. He said there's no way that this tiny team, then about 50 scientists and engineers at Caltech and MIT, can pull this off alone. There are too many things can go wrong. You have to have a much bigger team to deal with all the things that could go wrong. And so he built this LIGO Scientific Collaboration that now is a collaboration of 1,200 scientists and engineers at 80 institutions in 18 nations. And why was it that you really needed this? I can just give you a sense of how complicated these instruments are to deal with everything that might go wrong. Coming out of each of our interferometers today, there are 100,000 data channels, not 100, not 1,000, not 10,000, 100,000 data channels. Each of them telling you something about what's going on in the environment or various things that might go wrong inside the instruments. And we need all those to diagnose what's going on in order to be sure that if we see a signal, it's really a gravitational wave. And that's just a measure of the complexity. From 2000 to 2010, under Barry's leadership, we built the initial interferometers and then carried out our first gravitational wave searches. And we didn't see anything, which is just what I had predicted. And NSF continued funding us. Congress continued funding us. 2010 to 2015, we installed the advanced interferometers. Barry got stolen away by the high-energy physicists to lead another big project. And then we brought on a pair of superb successive directors, Jay Marks and David Reitz, who's currently leading us. In 2015, we began our first gravitational wave search. But first, before I talk about that, I want to say a little bit about these advanced interferometers. One of the most interesting problems with this is that with these advanced interferometers, we have to monitor the motion of mirrors to a precision of 10 to the minus 19 meters. That's the noise level that we have to achieve. And that is the same as the random fluctuations in the position of a mirror due to the laws of quantum physics. Now, let me be more precise. We have worked very hard to make sure that what we measure is the motion of the center of mass of a mirror. We do that by having very large beams that average, and huge numbers of photons that average over the surface of the mirror. And so we're really only measuring the average position of stuff on the surface, which reflects the center of mass motion, the frequencies we're working at. And so we have 40 kilogram particles. Now, if you have an electron inside an atom, it rattles around randomly and unpredictably inside an atom in a manner described by a wave function in quantum mechanics, wanders around at a level of 10 to the minus 10 meters. If you have a 40 kilogram particle, the random motion is a lot smaller. It's a billion times smaller, but that's the level of the measurements we're making. So we have 40 kilogram particles that are rattling around do these quantum fluctuations in quantum physics at the level of our measurements. And that is an issue. How do you deal with these random motions? For the first time in advanced LIGO, we see human-sized objects behave quantum mechanically, and we have had to develop, this was a prediction, we were first told about this by Vladimir Brzezinski, a great Russian physicist. We've had to develop what are called quantum non-demolition technology to deal with this. The key to quantum non-demolition is that you can control the fluctuations, the quantum fluctuations of these 40-kilogram mirrors by light pressure. And the light pressure, the random fluctuations of the light are due to something called vacuum fluctuations that enter backwards into the interferometer. And so you modify you control those vacuum fluctuations of light that enter backwards into the interferometer by a technique called squeezing. I just want to say the basic idea of this was from a student of mine called Carlton Case, worked out jointly by Bonnie Shoemaker in the theoretical work. And then the keys, steps toward implementation, Nurga Smelvavala, a young physicist at MIT, who was so good she got a MacArthur Award in connection with this work that she was doing. So here we are with advanced LIGO. Here are some photos of advanced LIGO, just to give you some sense from the air down inside the buildings. These are big vacuum tanks in which the mirrors hang. And you see the big vacuum pipes that the light beam is bouncing back and forth. And then Barry Barish has put a baseball player there, so you get some sense of the size of the instrumentation. On the right-hand side, you see a LIGO mirror. Now, we also needed to know something about sources of gravitational waves in our effort, because we needed to know what we were going after. And in order to be able to know what the signals would look like, in order to find the signals in the noise of our instruments. Already in 1980, I thought that the strongest sources of gravitational waves would be what we actually did see, colliding black holes. I estimated the strain that we would see, the gravity wave strain, would be 10 to the minus 21. That's what the numbers I've given you are based on. But we didn't know the shapes of the waves, the waveforms, and that's what we needed to know, how the waves stretched and squeezed as time passed it. And for that, we needed to have computer simulations. We could not solve Einstein's equations for what happens when black holes collide, because it's too complicated. We don't have the techniques with pencil and paper to solve them. We had to solve them on a computer, which is called numerical relativity. The efforts to do that began 50 years ago, at the same time as we were beginning to work on LIGO. By the early 2000s, I became very alarmed because the teams who were working on this could not even evolve two black holes going around each other, one orbit, without the computer crashing. And they'd been working on this for 35 years at that point. And I was worried. So I left the day-to-day involvement with LIGO to co-found something called the SXS collaboration with Cornell. It's the collaboration to simulate extreme space-times. SXS, simulate extreme space-times. Together with my former student Saul Tukolsky at Cornell. By 2005, the first successful simulations of the orbital motion and collision were carried out by Franz Pretorius, a postdoc in our collaboration, and then shortly thereafter by Joan Centrella and her group at Goddard Space Flight Center in Maryland, and Manuela Campanelli and her research group in Texas. And so three groups, all within 6 months of each other, finally had some success. 2014, then, simulations were mature enough for advanced LIGO's first gravitational waves searches. September 14, 2015, our advanced LIGO detectors were just preparing to start their first search. First search was supposed to begin 3 days from then, and the first signal came in. Fortunately, the detectors were on. They weren't fully tuned. They weren't quite in the state that we wanted for our search. But the first signal came in. We saw it. The director of LIGO said, "We are freezing the configuration of our detectors, and we are now in search mode." And we moved forward from there. First signal came in. These were the signals seen at Livingston, Louisiana, and in Hanford. The raw signals. The signals were so strong you could see them by eye. We expected them to be so weak you had to work hard to pull them out of the data, but you could see them by eye. This is the raw data, just bandpass filter to remove portions above 300 hertz and below 30 hertz. When the data were cleaned up, we had the gray band there, which agreed perfectly within the tiny amount of noise in the gray band, residual noise after they cleaned up, the numerical simulations from our SXS collaboration. And from then the comparison between the simulations and the observations, we concluded that you were seeing gravitational waves from two black holes. One of them was 29 times heavier than the sun. The other was 36 times heavier than the sun. The total mass was 65 solar masses. And the black holes collided, and we concluded from the comparison they collided to produce a final black hole that weighed 62 solar masses. 3 solar masses were gone as gravitational waves. It is as though you had annihilated 3 suns and turned all of the mass of 3 suns into gravitational waves traveling out through the universe. And we concluded that the distance was 1.3 billion light years. If we didn't have the simulations, we couldn't have concluded any of this. We had to have the simulations as well as the detectors. The movie that I showed you at the beginning, that comes from the simulations of the RSXS team. This is the movie that corresponds to the source that we did by comparing the observed wave shapes, the predicted wave shapes. However, what's really going on when the collision can only be understood if you pull back and look at our universe from a higher dimension. Now, the point is, the black holes are not made from matter like you and I. They are made from warped space-time. And to visualize this warped space-time, which they are made, we pull back. I take the orbital plane of the two black holes going around each other. That's a two-dimensional surface. And I want to look at it. It's the shape of that surface as seen from a higher dimension, from a third higher dimension. Each black hole looks like a funnel, and you've seen black holes depicted as funnels, so you've probably not been told this is what it would look like from a higher dimension. And these two black holes, these two funnels are going around and around each other, and the color coding is the slowing of time. Where shows red, time is flowing much more slowly than where it's green. And there are little silver arrows that are the dragging of space into motion by the gravity and the motion of the black holes. And as these two black holes go around and around each other, the time is in the upper left-hand corner. So these are a tiny fraction of a second. It's slowed into slow motion. The warp space goes into a gigantic splash, like in the ocean in a storm. And then it oscillates and dies out. The black is inside the black hole, and gravitational waves go traveling away. It is that gigantic splash in the shape of space and a corresponding enormous oscillation in the rate of flow of time that produces the gravitational waves. 3 solar masses of energy coming off in a fraction of a second. The total power output, the energy per unit time, during that fraction of a second of the collision, was 50 times larger than the total power output, the total luminosity of all the stars in the universe put together. 50 universe luminosities for a fraction of a second during the collision. The most violent, the most powerful explosion, astrophysical explosion that humans have ever seen except the Big Bang. But all we see is gravitational waves. We don't see any electromagnetic waves. So that was what produced the waves that we first saw. We have now seen 10 black hole collisions. This is just a little animation showing the 10 black hole collisions that we have seen. Some of the holes are big, some are small, some have big orbits, some have small orbits. They go around, collide, and merge. We have also, and it's important to know where the source of the gravitational waves is on the sky, so we can tell our electromagnetic astronomers to go look there and see if they can see anything. And so if you look on the screen here, our arrival, the information about where it is on the sky comes primarily from the time delay in the arrival of the signal at our two locations, Hanford, Washington, and Livingston, Louisiana. The first signal that we saw arrived in Louisiana first and then Hanford second, so we know the signal was coming from somewhere in the south, and that's how, looking at it more carefully, you conclude it was first hit the Earth at the Antarctic Peninsula. But with just 2 detectors, we don't get good information, but we get good information in just one direction. So we wind up with big banana-shaped uncertainty error boxes as to where the source is on the sky. So that's what you see in those big banana-shaped error boxes for 3 of those sources that we've seen. But down in the left-hand corner, you see one very small error box. And the reason it got small is we got a new gravity wave detector built by the Virgo collaboration in Italy. It's in Pisa, Italy. They turned on the 1st of August of 2017 and took data jointly with us for 1 month. And this last signal, called GW170814, we had all 3 detectors on, and now we could see where the source really was. And this was crucial in that just a matter of a few days later, when we saw gravitational waves from 2 colliding neutron stars. Each neutron star has a diameter of about 20 kilometers. It weighs about 1.5 times what the sun weighs. The density of the matter at its core is 10 times higher than the density of an atomic nucleus. And as the 2 neutron stars orbit around and around each other, emitting gravitational waves, they spiral together because of the loss of energy to gravitational waves. They collide, they merge, they create a gigantic fireball of electromagnetic waves that goes flying out into the universe. This is called a kilonova explosion by astronomers. And indeed, we saw first the gravitational waves, and on the left is the gravitational wave signals of the 3 different sites displayed in a manner I've not described before. That's not important. The key thing is that 1.7 seconds later, we received a burst of gamma rays here on Earth that was seen independently by 2 different gamma ray telescopes in orbit above the Earth. And then over the next few hours, electromagnetic waves of ever lower energies came in. First X-rays, then ultraviolet, then optical, infrared, and radio waves. These were all seen by electromagnetic astronomers. This was the most, and the electromagnetic astronomers knew approximately where to look because LIGO told them, because we had 3 detectors working. They went and looked. The gamma rays, they didn't have very good angular resolution, but the other electromagnetic waves have good enough resolution that you could even pinpoint which galaxy they were coming from. And so, with all of that information, this was the most studied, most observed event in the history of astronomy. Something like 15 or 20% of the world's astronomers all studied this after LIGO gave the information that it had seen these waves. This is what we call multi-messenger astronomy, because each of these different kinds of electromagnetic and then gravitational waves contributed. And by analyzing the electromagnetic emission, it was possible to verify a prediction that had been made in the past by theorists, that there was huge amounts of gold and platinum and other precious metals created when the 2 neutron stars collided. And in fact, you can then extrapolate to other neutron star collisions and conclude that most of the gold and metal that we see here on Earth came from collisions of neutron stars. So this is an example of what we're getting out from gravitational wave astronomy. Well, I want to very quickly tell you about the future and then wind up. So there will be huge improvements in LIGO and the other ground-based gravity wave detectors over the next 2 decades. By the 2030s, we'll be seeing 20 times farther than we do today. That means the volume of the universe is 20 cubed or 10,000 times greater than we see today. We'll be seeing every black hole collision in the entire universe, going back to the beginning of the universe, with masses less than 200 solar masses. We'll be seeing many, many other kinds of things. There are bound to be some very big surprises. Also, by the 2030s, there will be 4 types of gravitational wave detectors operating, each measuring gravitational waves with different gravity wave periods. Millisecond periods, LIGO and its partners here on the surface of the Earth, such as Virgo. Periods of minutes to hours, an analog of LIGO in space. 3 spacecraft that track each other with laser beams, called LISA and later the Big Bang Observer. Radio astronomers using a technique called pulsar timing arrays will be seeing gravitational waves with periods of years to decades. And then a technique that I won't go into detail, but it's called CMB polarization. We'll be seeing gravitational waves with periods of hundreds of millions to billions of years. Now, a student doesn't live that long to analyze the data. And so what we see is a pattern on the sky of polarization of this cosmic microwave background. But I don't want to go into the details. But also by the 2030s, the really interesting thing that we expect to be studying is the birth of the universe, studying gravitational waves from the Big Bang itself, from the initial singularity that gave rise to everything we see in the universe. And we expect to be watching the birth of the fundamental forces in the universe, not just the birth of the matter that we see in the universe, but the birth of the fundamental forces as they came into being in the early universe. So let me conclude by saying again that it was Galileo who started electromagnetic astronomy 400 years ago. And LIGO has started gravitational wave astronomy 3 years ago. And when you contemplate the enormous changes in our understanding of the universe that have come from electromagnetic waves, I invite you to speculate about what will be the things we learn from gravitational waves over the next 400 years. Thank you.
Thank you so much for that wonderful presentation. We do have time for a couple of questions before Dr. Thorne has to go. So if you can please stand up or raise your hand. Either myself or Rebecca Gerton will come and come to
Rebecca's
the microphone.
back in the back there.
Yeah. So.
I'm curious. The speed of electromagnetic waves is the speed of light, which is capped. What do you know about the speed of gravitational waves, and what impacts that?
So we know that general relativity predicts they should travel at the same speed as light. And we actually have observational data from this neutron star collision, where the gamma ray burst arrived 1.7 seconds after the two neutron stars collided. And so, and it should have been produced within a few seconds of then. The fireball was initially opaque to gamma rays, and it took a second or two for it to cease to be opaque to gamma rays, and the gamma rays could get out. And so we would expect a delay of about what you saw of about 1.7 seconds. But all we can say then is that the two waves, gravitational waves and the gamma rays, which are electromagnetic, they propagated at the same speed to within the ratio of about 2 seconds divided by the distance, which is, I think, 40,000 light years. 2 seconds divided by 40,000 years is the accuracy with which the propagation speed was the same. And so, let's see, a year is 3 times to the 7, 40,000, 11. It's about within a part in a trillion, roughly, from that one observation. So Einstein was right on to within enormous accuracy in his prediction.
I'm Mark Horstmeyer, the Dean of Liberty University. Wait a minute, a very awesome talk. And I think for all the engineering crowd here, we were always taught physics always came before engineering, but I think you proved to us tonight it was the engineering that helped show what the science was. So that was beautiful. My question is about the rotations. We see these rotations in the solar systems and the galaxies everywhere, and you showed them tonight. With these neutron stars, everything coming together. Where did all these rotations come from, and what started that?
So, of course, we know about that once you have something that's rotating, its angular momentum is conserved, unless it radiates some away or something. But basically, angular momentum is conserved, setting aside possibility of losing a little bit, say, by some emission. And so if something that is big is rotating very slowly, of course, as it shrinks, it rotates faster and faster. So the question is, you begin with the universe, you had some big inhomogeneities in the universe, big lumps, and they somehow started rotating very, very slowly. And where did that come from? And you can ask the same question of where did the lumps come from which the galaxies ultimately condensed out. You had to begin with some irregularities, both in terms of a little bit of rotation and a little bit of lumps. As best we understand this, this is an analog of Hawking radiation. That in Hawking radiation is something, if you have a black hole, because there's a horizon beyond which you can't see, at that horizon there's a random creation of tiny amounts of radiation that go flying off from the horizon of the black hole. Similarly, in the early universe, there is what we believe, and there's strong evidence of this, that there was an inflationary era of the early universe when it was expanding very rapidly. And in that era, there was a horizon. There was a boundary beyond which you couldn't see because the universe was expanding faster than the speed of light out there compared to us, and light couldn't reach us from there. And random fluctuations that came off of that boundary beyond which you can't see, which are demanded by the laws of quantum physics, that appears to be what ultimately gave rise to the lumps that have made galaxies. And it works out quantitatively. Also, I think, though I've not seen the numbers done, to the rotation as well, the tiny amount of initial rotation that you needed in order to get things going. Of course, once you have a little bit of inhomogeneity, you can then get additional rotation through things like shock waves and so forth. But anyway, that's where it all probably began. And it's awfully esoteric, but it illustrates the fact that these fluctuations, these random fluctuations, that we're dealing with in LIGO because the mirrors bounce back and forth at a level that we have to control. And we control it by random fluctuations of light. These random fluctuations play a huge role in the universe, and they probably were responsible for the lumps that made the galaxies and for the rotation.
Thanks, guys. Not at all.
So you're talking about seeing back to the Big Bang. I'm guessing you're seeing reflections. What is the waves reflecting off of? And also, how are you theorizing what those waves of the Big Bang will look like? Okay. I'm not sure how you computer model something that we don't really understand that well.
Okay. So there is a standard prediction of what came off the Big Bang. And the prediction goes like this. This is what is believed by most of my colleagues, the deep theoretical physicists. That what came off the Big Bang was just these random fluctuations that I referred to as being like Hawking radiation. But that during this inflationary expansion, where the universe was expanding extremely rapidly, that very rapid expansion amplified the stuff that came off the Big Bang. It's an analog of parametric amplification that you know that is used in parametric amplifiers in technology. And so there's a parametric amplification of what these random fluctuations that came off the Big Bang. That's what makes them big enough to make. And that's what, in terms of the size of in terms of the amplitudes of the lumps, and makes gravitational waves strong enough that we do expect to detect them during the coming decades. By the 2050s, I expect that we will be seeing these primordial gravitational waves in two widely different frequency bands. First, the bands corresponding to periods of oscillation of hundreds of millions to a billion years, using so-called CMB polarization, and then directly oscillations with periods of a few seconds with a space-based gravity wave detector. I expect and I hope that what is observed will be different than what this theory says. I think I have seen several times in my career things that we really believed rather strongly as physicists turn out to be wrong once we got experimental data. One of them is the unexpected so-called accelerated expansion of the universe today. I didn't believe it until there was so much data that my nose was rubbed in it, and I had thrown the towel. I think there's a very good chance that when we see these gravitational waves from the Big Bang, they will not agree with the theory that says you began with random fluctuations that got amplified by inflation. And if that's the case, then it's going to be very exciting as we try to scramble as physicists and cosmologists to figure out what really was going on in the Big Bang and how did we get it wrong. But that's my hope. I'm always hoping for things to go wrong. For things to go wrong in terms of our predictions, not in terms of our experiments. Yeah.
What you're saying is, what if we can't explain? You're hoping was the Big Bang.
Well, what if for the details of the Big Bang, I'm hoping that our explanation of the details was wrong. I think it's incontrovertible that there was a Big Bang. But the details that enable us to say how strong the waves are coming off the Big Bang, and I'm hoping that we got the details wrong, and that's going to tell us something very deep about the laws of physics that control the Big Bang. I think that's fairly likely. I mean, this is a prediction I made in my Nobel Prize lecture, and I hope I live to see it come true. I think it's getting late. Do you want to?
I think we're going to ask this question and potentially
Okay.
one more.
So, sorry. So in English, what is on the other side of the black hole, and why won't the black hole just like suck in the other black hole? Why do they actually collide?
Okay, so that's two questions. But I'll try to answer them both. First of all, what's on the other side? By that, I think you mean on the other side of the horizon, down inside the black hole. And down inside the black hole, according to our understanding of Einstein's relativity, down inside the black hole, there are three objects that we call singularities. That's three different locations where the laws of physics, as given to us by Einstein, fail, where the strength of gravity and the strength of the warping of space and time are so big that Einstein's laws can't deal with them. And they can't deal with them because when the strength of gravity gets that big, the laws of quantum physics come in and these fluctuations start getting huge. And so you have to have the new laws of quantum gravity that combine quantum physics with Einstein's laws of warped space-time. We have to have those in order to understand that. So there are three singularities of this sort inside the black hole. And the Big Bang is a fourth such singularity. It was also controlled by these unknown laws of quantum gravity, ill-understood laws of quantum gravity. And so I discuss these three singularities inside a black hole in my book, The Science of Interstellar. So if you just go look at that book, I have a detailed discussion of them. It's only in the last several years that we have understood there are probably three such singularities inside the black hole. And so the second issue is when the two black holes come together, there's general relativity. There we understand the prediction. General relativity says that they will merge to form a single black hole. They come together because they lose energy to gravitational waves. As they lose energy, it's like friction. They spiral together closer and closer. They collide and they merge, and you wind up with a single black hole. What happens to the three singularities here and three singularities there inside the two black holes when the two black holes merge to form one? We don't know. We need computer simulations to try to figure that out. But it's the collision of the two black holes. They merge. And the computer simulations show that merging, and we can understand all the details of what happens outside the surfaces of the black holes by solving Einstein's equations on a computer, and so that's what we do with this SXS collaboration. Okay.
Please join me in thanking Dr. Thorne once more. Thank you once again for being here as part of the Engineers Week at Sweet Briar College. Safe drive home.